So today I will be talking on product development and metallurgical issues in additive manufacturing. So product development, how we have to go for if we want to develop a new product, or we have to make some changes in the product. So there will be some some talks on this. And in metal additive manufacturing, there are always some metallurgical issues which we have to keep in mind when we work with additive manufacturing, particularly metals and alloys. Before going in detail, first of all, let us see this slide. Are you able to see this slide?
Yes, sir.
Yes, sir, it is visible, yeah.
Yeah. This next slide, here we have a blacksmith and one clay pottery. So what happens in age-old times, blacksmithy was known to people, and clay pottery also was known to people. But do we know that whether they knew the science behind it? So they knew the technique. They discovered a technique to make sickles, make earthen pots, earthen lamps, but they were not able to see, understand the science behind it. So they discovered, they might have discovered with experience or by chance, and they started using it. But the era we are living in is basically the age of science, where we go into the material, into the processes, and know what kind of processes give rise to what kind of microstructure or properties to the material. Based on that, we try to develop products for the benefit of the mankind. So in this process, what happened? There was the there was the first industrial revolution in the year around 1780s, where what happened is, where we were using only the manual labor or manual energy to do something, that was given to the steam engines and other processes. And later on, we shifted to second industrial revolution. I think mobile is slow, so just a moment. Yeah. Second industrial revolution, where a little bit of automation was put in the materials, and you can see that this happened in the Then after, there was a third revolution, industrial revolution, where full automation took place and the production rate of the products increased. That is the third industrial revolution in 1970. Today, in the first 21st century, in the beginning itself, we witnessed a fourth industrial revolution, what we know actually as Industry 4. And this fourth industrial revolution used the physical system as well as the cyber system to bring in the large amount of flexibility with the production process. But what happened, if you look at very carefully, then these processes which are coming up now, and those processes which were being practiced by many other people, other industries, there is a lot of difference. Difference in economics, difference in the supply chain, and different in the market. So what happened, this new development in the industry was industrial revolution. There is bound to be a technological disruption as well as market trauma. I would request you all to please mute your microphone, please. Please mute your microphone, please. Yeah. So we have to be very careful with these new developments in the industry, in the technology, and the science behind it. Now, if you look at the new developments starting from 15th century to the 21st century, we had witnessed several major technological advancements, right from the printing press in 15th century to electricity, medicine, telephone, computers, internet, and we have after crossing all these advancements reached to 21st century where 3D printing has been proved to be one of the most promising processes to to make the products which are really not possible by any other processing techniques. Now, we should know what is additive manufacturing actually. So, what is additive manufacturing? So, simple definition gives process of joining materials to make objects from 3D model data and usually layer upon layer. So, if you look at two different processes, what we had been doing today up to now was two manufacturing processes, that is formative manufacturing and subtractive manufacturing. In formative manufacturing, you know, being a student of mechanical engineering, that casting is called formative manufacturing, where you have a die, then you pour a melt in the material, and when it solidifies, then you take the material out. You can see this picture. Yeah, you are taking the material. This is formative manufacturing. Then there is subtractive manufacturing, where you take the block and then use your machining tools and give a shape to the material so that you reach to the desired product. But in additive manufacturing, this is totally different. You do not use a liquid or dye or something, or you do not use any machine tool, but you just use a raw material in liquid form or solid form in the form of powders or sheets or powder sheets and wires, where you can see that you build the product layer by layer. You start from depositing layers and you build up and finally come to the product. So this is called additive manufacturing. So you can understand that right now formative and subtractive manufacturing is taking a backstage, and the additive manufacturing is becoming easier to operate for the people. And the most important thing is you can make very complex products using this technique, because you do not have to depend upon die making or the tool movement. Okay. See a sculpture puzzle. Here you can see Dr. Sharma.
Yes, sir.
Am I audible?
Yes, sir, you are. Yeah, yeah. The
Okay,
screen
okay.
is also
Okay.
visible.
I just wanted to check in between. Okay. So if you look at this, these are
Yeah, that's fine, sir. That's all right.
okay. These are the puzzles where you can just imagine you have a model like this, and you want to make this model using different layers as you are doing in additive manufacturing. So what you do, you divide this whole model in different layers, and you put on different layers according to your requirement to build this whole body. So this is what happens in a additive manufacturing process. You take the product, but in a computer, you divide in different layers, and your computer knows what different layers, shape, and thickness are. And using the tool, the additive manufacturing machine, you develop those layers one by one over each and every level of the material, and finally you get the material. Now, what do you require in additive manufacturing? So there are four main things. That is control, where you have to have a CAD file, that you can make CAD file by your own design, CAD design, or you can take any product, do reverse engineering, and come out with a CAD model. Then you can divide it in different layers and think of what parameters you should use so that you are successfully able to make a product. And what are the inputs in this? You have to have raw materials, for example, powders or wires or liquid, or a liquid in case of polymers only, liquid or wires. Okay, and there are other utilities you understand, and there is a substrate. On the substrate, you start building the material, building the product. Then there is AM machine here, and this AM machine uh, builds it for you, and finally you get a block or product, you can say, or the substrate will always be there, and then there will be exhaust gases because you do additive manufacturing in a closed chamber where it is filled with gases, and obviously some powders or sheets will not be used in additive manufacturing process, and so this will be treated as waste. So here you can look at in the next slide that you require a digital model of the product, and you require materials, this is liquid droplets, wire, sheet, or powder, and you require tool for laying material, that is AM machine, and a digital control system for the tool, that is sensors, 3D movement of the nozzle, and all those things. All the laser beam, all those things are necessary. These four things are necessary to have a successful additive manufacturing, to produce additively manufactured product. If you look at the evolution of additive manufacturing, that is called 3D printing also, then it started basically in 1984, and there was different developments at different stages. In 1984, it was the first process by polymerization of liquid polymer, and that gave a feeling that how a 3D model can be produced using a liquid polymer by photopolymerization. And finally, we got the printing machine. Printing machines in the market in the year around 2008 or before that. And then we started manufacturing products in 2014 onwards. This is the evolution of 3D printing. And what it looks like, how it takes place. So just to give a feel of this, I am taking four different processes for liquid, powder, wire, and sheet. And you can see that here a liquid precursor is there in a beaker, and just a moment, that is in a beaker. And now your computer knows what should be the first layer of the product. And there is this, there is a photo UV laser light, and as it falls on the polymer, polymer is cured and becomes solid. The moment it becomes solid, it is brought down, and new liquid comes up, and on on that a second layer is cured. So if it keeps on happening, finally, after so many different layers are cured, you get the final product. This is if you have a liquid precursor. Now, if you have a powder precursor, then what do? Here, this is a substrate. You put in one layer of powder here like that, and then you use laser light, and this laser solidifies the first layer of your product here. And once this is solidified, then you put a second layer of powder on this, and then once you put the second layer, then the second layer known by the computer will be printed on the first layer. So that way you will be able to produce in so many different layers. If you have thousands or 2,000 layers of materials you put, and then you get the product. It depends on the size of the product you want. Okay. Now, if you have wire precursor, just example for in the case of polymers. Here also you have a wire. Sorry, you have a wire here, and this is being extruded through a nozzle. This is a nozzle. This is generally heated, and when this wire passes through this nozzle, it becomes almost liquid, and then you start building layer by layer like this, as we had been doing earlier. So layer by layer using wire precursor, which is extruded up, and heated and extruded, and then you get the product. Here are some small lines you can see here and here. These are basically the supports, because if you want to develop this part like this or this part, and then you need a support to make them stable, your product is stable. These supports are very small and very thin in size. Once you make the product, then you can just take them out or break them out. Okay. Then sheet metal precursor, if you have, so you have a coil of sheet here, and this coil passes through a heated coil, and once it is heated, here you use a laser and cut different layers. This is the first layer of a product, then second layer. So you keep on cutting those layers from this whole sheet and laying one by one. And this requires proper sintering and proper joining so that you get the final 3D product after sheet precursor, using sheet precursor. Okay. There is one more important process. This is important process that is called binder jetting, where you don't use any laser system or any extrusion. What you do is you take the powder, just here only, layer by layer you are putting in, and what you do is you use one binder here. This binder is coming, and layer by layer it is just binding the powders. This binding can be done for metals, ceramics, as well as polymers. And once this is made, this product is made, this is not the final product, this is a green product basically, because it will not have strength. So this part has to be sintered in a given environment so that you can get the desired part in the sintered form. From this to the sintered process, there is a little bit of dimensional changes. So you have to take care of those dimensional changes which may take place after sintering. So you have to give a tolerance in your product design before you start using binder jetting. Okay. So, so here just an example of what is the difference between subtractive manufacturing and additive manufacturing. So just think of that you want to produce some bolts. So for bolts, you require some wire. We call it wire rod basically here. Oh, sorry. So wire rod, then you do some cold forging, then you form the bolt head, then you start threading it. You can thread it by rolling or cutting, and after that you do heat treatment to give the strength to the bolt, and finally the surface treatment. So many different processes are involved in making a bolt. Though the production rate is very high, but you have to have so many processes. But in additive manufacturing, you need to have a design of the product on a computer. You should have a printing machine, and you can directly print a product. The properties of these products may not be as good as you want, as you get in subtractive manufacturing, but there requires some post-processing to be done on these products which are additively manufactured. In some cases, it is very, you can use it just after surface finish, but in some cases where you want it to be load bearing, you have to do some post-processing of the material. Now, after this, we can summarize the whole process of additive manufacturing as follows. So, if you have a part here and you want to make this part using additive manufacturing, so what do you do? First of all, you make a CAD design, you make a CAD translator, translate the CAD design. So finally, you make a CAD model of the product, and after that, you make the file suited for the additive manufacturing machine. So you verify your file so that whatever you have designed, is it exactly coming as in the product or not, or what kind of supports you require to make that part, and what parameters, process parameters of the machine you should use to get the desired shape of the product. After that, you have to ensure the material, what material you are using, the chemical composition should be the same, what you want, as well as the physical properties should be known a priori of the before you go to additive manufacturing process. Then you make the build. Yeah, then you go to additive manufacturing machine and start building the product layer by layer. And finally, once you are done with the product manufacturing, then you have to do post processing, as I just told you in the last slide. And in some cases, post processing may be required, where you have to clean it, you have to remove the support elements, or you may need to go for some heat treatment, some curing processes like in binder jetting and other processes. I think up to now I am clear. And now we go to different processes what we have in the market. So there are different processes. The first of all is direct energy deposition process, where you give a laser or beam which has a focused thermal energy, and this thermal energy where there is a laser, then you put powder in this, and powder is melted, and fused material is deposited layer by layer. Then you have powder bed fusion process, as I just showed in the powder process pictorially. That is powder bed fusion, means you create a bed of powder. The first bed of powder, then you use laser and make the first layer of the product. Then you put the second bed of the powder, and then make the second layer like that. Then there is a binder jetting. I just explained to you that this requires a liquid bonding agent, and liquid bonding is used layer by layer on the powder layer. Then there is material extrusion, where in this case, just for the ceramics or polymers, you can use it. And in this process, and material is selectively dispensed to a nozzle or orifice, as I showed it to you in the slide describe the wire process. Then material jetting here, in this case, you make the droplets of material, like in case of polymers, this happens, and the droplets are selectively put on the selectively deposited. And here you don't require a powder, you just require droplets putting on the first layer, and then once that is cured, then you put the second layer of droplets. So here you don't require putting a bed of powders, but simply droplets one upon other, they can develop into a product. Then sheet metal lamination that I have already described it to you. Then wet polymerization that also I described to you in liquid process where you have a liquid photopolymer, and liquid photopolymer is cured using light activated photopolymerization. So the next thing is uh, what kind of just to revisit these processes and what happens, how they can be used, what material you can use. So raw materials and processes, feedstock material, what you can have is liquid or solid, and what forms of this feedstock can be. So they can be powder, they can be filament, they can be sheet, and liquid doesn't have any form, so liquid will always be there. And then uh, what are the principles in all these different processes? So in a liquid, you can have polymerization, and also you can use binder like that. Okay. But for powder, you can use binder jetting, or you can use melting and freezing. Just like when you use laser, then you actually melt the powder, and that is solidified. But in the same powder, you can put binders here, and binders will give bind the material to the 3D product, but it will not give a strength. So after this, you will have to go for uh, sintering or curing, and this is mostly used in all ceramic as well as the metals. Then filament, again, melting and freezing is required. Same process can be used. Same principle can be used for this. And sheet, there is no other joining process, only joining from surface to surface. So these are the processes. Now, what are the AM processes we call? These AM processes are uh, the wet polymerization for liquid, and binder jetting and material jetting. After you use binder in the with the powders, then you can use these two processes. And melting and freezing, there are three different processes. That is powder bed and directed energy deposition and material extrusion. But for sheet, it's the sheet lamination. That is the whole AM processes that can be used for liquid as well as solid. And this picture shows that which process is good for which material. So here you can see uh, in the first left, dark green here like this. So that means polymers are basically mostly done by wet polymerization, and binder jetting and in the liquid form basically. And if you have polymers in the form of powder, then you do binder jetting or material jetting. And here these three different colors, they show that darkest is more suitable, and as it becomes lighter, the suitability of this process decreases. Okay, same here, this powder bed and DED. This cannot be used for polymers, but ceramics and metals are frequently using these techniques, and you can see metals are more preferable compared to ceramics for these two techniques. Similarly, for material extrusion and this, for metals, basically sheet lamination is used, but for polymers and ceramics are not generally used in metal extrusion or sheet lamination, but polymers can be. So this is giving a very good whole picture of what happens and what are the processes, raw materials, and AM principles, all those. So now we come to some products. What products are made by these techniques? So applications, you can go for prototyping, You can go for low volume manufacturing. You can make tools, consumer products, and you can make some products you customize to your own needs. Even at your home, you can uh, make some products according to what shape and size you want, because if it is not standard and it is not being produced in the market, then you can yourself personalize such products for yourself. You can make art and designs like this, and you can use this process for educating students. Now you know that there is the Government of India skill development. They are using Atal Tinkering Labs, where they have this kind of uh, 3D printing labs, and they are teaching the students about 3D printing in schools. And you can use this in medical industry, where you can make flute, you can make orthopedic parts, and also you can make the skull parts. So there are some people, just for example, if somebody had an accident and some fracture goes on in the head, so immediately doctors that they do a CT scan, they find which part is fractured, and they can immediately print that part and fit in. So these are the applications of 3D printing, and so you can see these are the products from ceramics, from plastic, and from metals. I don't want to go in detail of this. For metals in particular, many of the materials are being used for engineering application. For example, you see this is the hydraulic valve made by stainless steel. This is titanium heat joint, titanium alloy hip joint, and this is a heat exchanger made of copper. This is induction heating coil by copper. So many of these alloys and materials are being used to make engineering products. And in brief, we can say that if you have metal AM, then what are the advantages? So first of all, there is freedom of design. Means you can sit on the computer, you can design whatever you want according to your need, or if you like some product and you want to copy it, you can go for CT scan, you can bring it in computer and just try to print it. So this is the freedom of design. And there is complexity for free. If you use formative manufacturing or subtractive manufacturing, you are limited with the processes. Some intricate shape you simply cannot make. It's just impossible to make by conventional processes. But in this additive manufacturing process, you have that flexibility that you can make any complex um, part. And that also gives you an advantage, because we use different fasteners in the industry to bring in some new mechanism. But what happens? These fasteners add to the weight of the material, to the product, and also these fasteners add to the number of the components. Okay, so to avoid these fasteners, what you can do is you can simply bring all these things together and design it, and you can have one single product where you don't require any fasteners at all. So this is the one thing. This is the other thing. Just here you see this is part consolidation. You have so many different. You can make uh, different parts of this pipe, for example, and then you have to fasten it. But if you use additive manufacturing, you can make this shape in one go like this. So you avoid the fastening. Similarly, you can make lightweight designs. What do you mean by light? I mean by lightweight design is, in some cases, what happens that if you have a solid product and if you have to use it and you want the dimension to be bigger, like metallic foams. Metallic foams are light and they have a different application. But if you want to make a metallic foam kind of thing, all the materials with minus Poisson ratio, that also you can make by this process. Then AM can be used for many other processes. For example, you want to make dies with internal cooling, then what you do? You have to make so different arrangements if you want to make those dies using conventional routes. But in the AM process, you can make channels like this. You can see here green channels like this, or here in the green channel here. So inside the product, you have channels where you can pass your coolant, and your material will be safe. Your material will have longer life, and all of this. For example, forging dies. There you can always use such processes. And second is additive manufacturing in metal casting, for example. So we know that in metal casting, making pattern and making pores is a very difficult task. And in this process, AM, generally people use binder jetting, they use sand as it is, and sand is used for additively manufacturing the patterns like this. And these patterns are made in such a way that they are the negative part of something. And then when you make a CAD model, you make negative and then you make positive by during. So part design in CAD, 3D solid model is inverted to make a negative of the part. So you make a part and then invert it, then you get a pattern and also the core, and that can be used for making a second positive as a product. So, and this gives a design freedom also for making the patterns and codes. Okay, but one thing I would like to mention here is which is very important. That is when to use additive manufacturing. So additive manufacturing should be strictly used only for very complex systems, complex products. Because if it is not complex, then you can use the conventional routes of manufacturing. And if you use traditional fabrication process, manufacturing process, then the cost increase with the complexity increases like this. If you are making more complex parts, then cost increases like this. But if you are using additive manufacturing, the cost increases like this. So, what is the advantage? If you have more and more complexity and you want to make more and more number of products, then additive manufacturing will be cheaper compared with the traditional process. So, that gives a message to us that we should be taking up additive manufacturing only when the parts become very complex, or we want to reduce the weight by combining different parts into one. So I don't want to go in this. So now I come to the metal additive manufacturing. In metal additive manufacturing, there are, as I told you, there are different things. For example, there can be load bearing as well as non-load bearing products. So if you have non-load bearing products, for example, as I showed in the bottom, this is heating coil, induction heating coil, or heat exchangers. They are non-load bearing components. In non-load bearing components, what they can do is they can serve the purpose, but they cannot withhold any loading on them. But if you want to load the product, then you have to have so many different properties that has to come with that. That is microstructure and phases you have to control. You have to control the texture. You have to control the mechanical properties, for example, creep resistance, fatigue resistance, strength, ductility, all those things. Okay, so there are two ways. So what happens that in load bearing components, if you want to concentrate on the mechanical properties, then definitely you have to look at the microstructure very carefully. So this is a process where you design a material or product, and you have some equipment and you know how to operate it, and then you make material and measure the performance. But what happens, you can go in two ways. Either you do it on your own without knowing any science behind why you are doing something, or you can know the performance you require in your product, and then you slowly, by knowing everything, what happens, what is science behind it, and then you go to equipment and build the part directly. So there are two different ways. One is science-based methodology, where you know the goals and you know the means. That is called inductive inference, and then by chance, if you produce something, that is, you have the experience, as in the second slide we saw, making sickles and earthen lamps. So those are the discovery and experience. So you know what causes what, and then finally you get the material for yourself. But if you are doing science, you have to have the knowledge that if we want such and such performance, then what we should do. So you should know the goals and means of uh, your product, and then you use your science understanding and then go to the equipment. So additive manufacturing, metallurgical manufacturing is basically done by two ways. One is powder bed process and DED, and they look like this. In the left side picture in the bottom, you are able to see this is one layer being fused using a laser light, laser beam, and the second one, there is a directed energy electron beam or laser beam that there, wherever it strikes the substrate, uh, powders of the material goes there and fuse, and this is how you get the product. But what happens that in the process, when you apply the high energy beam on the powders, there are different processes happening. That is, a large amount of heat is coming on the powder and it is melted. Some elements may evaporate, some may radiate, and there are different kinds of things happening. Some powders on the sides of this, for example, this is melted, heat is going through all these processes, all these areas, and some powders are still unmelted or not fully fused. So this is the condition of a liquid pool once you supply energy here on the powder bed. So what happens if you have a first layer, for example, this layer here where the material, where the laser beam strikes, it is melted and this area is also heated, but the temperature is slowly decreasing as you go away from the point of strike. But as you increase the thickness of the product, as you go up layer by layer, then the area heated becomes more and more. So that means all the part which has already been deposited may be further affected by the heat of the process. Okay, this is one thing. And the second part is that once you melt the liquid, just to say this is powder layer and this is a substrate, you melt the liquid, this is a liquid pool, metal pool forming, and as the energy increases, this forms. Okay, this big liquid pool forms on the surface. We call it prior liquid pool. This liquid pool, here is a substrate, and there will be some nickelation here. So what happens, this liquid will solidify, will become solid. But during solidification, there may happen two things. Two things here are either you have new nucleation of new phases, or it may solidify on the previous layers of the solid. So there is a competition between nucleation and the growth of already existing processes, already existing microstructure or grains. You see, you can please switch off the. Please mute your microphone. Please microphone. Yeah. So here you can see there is a directionality in the microstructure. So this directionality basically comes from process. And here you can see that one of my colleagues, Dr. Gopalakrishnan, he had done some work on stainless steel. And here you can see he printed this block, and you can see the microstructures. The microstructure, this one, it is coming from directly from normal conventional route, but these microstructures are from different sections of the block shown above. So what happens that different microstructures in different directions, so they give rise to a kind of a directionality in the material. So this directionality in the material generally is not good for the mechanical properties, or it may give rise to anisotropy in the material. And this is why metallic component, which is load bearing, there are some issues which has to be dealt with proper control of the parameters and proper knowledge of the effect of the process parameters on the microstructure. So what happens that to address these problems, people devise different ways of using lasers. So we call it laser scanning strategy. You can see in this case, laser goes in this way, then comes back and here. So there are different ways you can use your lasers. Here you can see last one, chessboard. So if you use this kind of laser processing, then what you get? You get, though you will have anisotropy, but this will be very local in region. So anisotropy as well as the inhomogeneity in the material due to the thermal stresses or due to compositional variation may be reduced if you use this kind of laser scanning strategy. Possibility that once you get the different directionality in your microstructure, you can always go for post-processing like heat treatment and other process to change the microstructure according to your requirement. But this may not be at all be useful. That we have to see that which material we are using and what is the effect of different heat treatment schedules on these materials and whether it is heat treatable or not. Those things, issues are there. Now I come to the brief on AM metallurgical issues. What are the processing defects? You can see. So there can be loss of the element. All the elements which are having low melting point, they may evaporate from the bed, and finally your composition may not be that what you want. And there may be some porosity or lack of fusion. There may be some gas entrapment in the material during melting, or as I showed you earlier, some powders may not be fused altogether, or they may not be properly sintered also in that. So if they are not fused, so they will be separate and they will be seen in the microstructure in the form of pores. Okay, and then surface roughness. Surface roughness depend upon the what is the energy you are using for your additive manufacturing, or what is the powder size you are using, or what is the layer thickness you are giving. Layer thickness means layer thickness varies from a very low 20 micron to around 100 micron. Layer thickness of powder, and these things may be determining what would be the surface roughness of your product. Very due to different solidification route and different temperatures in the material, there may also be some in situ phase transformation in the material. So due to phase transformation or due to thermal stresses, there may be some stresses in the product, or some thermal or some distortion may take place in the material. So all these things have to be taken care of during the additive manufacturing process. And anyway, though we say that we are quite advanced in additive manufacturing, but it's my personal view that so far as load bearing the products are concerned, we have not gone very far off. Though people show products with very good mechanical properties, but even then, the literature says we have to go a long way. Then there are solidification defects in the material. I am not sure you people are the students from mechanical engineering, but I don't know whether solidification part is there in the curriculum or not. But there are some anisotropy in the material due to additive manufacturing and solid state phase transformation, and there are some microstructural inhomogeneity. So all these defects may lead to different kinds of mechanical instability in the material. So these have to be solved. Now I come to metal powder. I have only 10 slides left, 8 slides. So I think time is also coming up. So the thing which I want to mention here is the Indian situation. Metal powder for AM of metals and alloys are very important. So right now, whatever powders we used to have in India, that is particularly imported, or there are one or two companies. GKN is there in Bangalore; they are producing it. But for a widespread use of AM, I personally feel that we should have much more emphasis on powder production within the country. And there is one more thing, that all the powders which we are getting right now, they are basically meant for the powder metallurgy route, but in AM we get a very high solidification rate, and we can have a different composition altogether suited for AM of the material. So there are two things, in-house powder production in India, as well as we should have lab scale powder production units where we can play with the composition to produce powders, and we can test those powders with a new composition, that how these powders are good for AM. Okay, so here in this next slide, you see what are the characteristics of a feedstock material, that is metal powder. They should be very small in size. They should be very spherical. There should be good flowability. Flowability means if you have a mass of powder and if you just tilt the beaker, it should flow very smoothly. And it should have narrow side distribution, means the powder should have the powder sizes not in a very wide range, but in a very small sizing. So that is one. And there should be no contamination. It should have a proper composition and no gas balls. So these are the requirements for metal powders, and there are different powder processing routes. Here we can see that in the first one, this is gas atomized powder, this is centrifugally produced powder, and this is rotating electrode powder. So different processes of powder processing have different advantages and disadvantages. But I would like to mention one thing, that the prep process, that is plasma rotating electrode process, is basically used for very high melting temperature materials, for example, titanium and tungsten and all those things. And nowadays, gas automation can also be done by for titanium alloys, but that requires a very careful processing. So what you can see here is the next slide. In the left slide, you can see this is the powder producing unit where you have induction melting furnace, you have a nozzle here that is called atomizer, and once the atomizer interacts with the liquid, then you get fine droplets, and these droplets, if allowed to solidify, they give rise to powders. These powders may have very wide side range, so you have to deal with the process parameters, means what kind of gas pressure you are using, what kind of nozzle you are using, and what kind of liquid temperature you are using, all those things, what is the surface tension of the material, whether your gas is hot or cold, all those things parameters determine the size and distribution of the powder. The second route, what is given here in the right, is for very high melting temperature materials. What you can do is there is an induction coil here. So no, this is a rod, induction coil, no contact with any material. And once this is melted, directly coming to the zone of automation, and you have gases coming. Okay. So this is the other process of powder, and this is you are using wires of some materials, and here you are generating a plasma torch, and this plasma torch, due to very high energy transfer, you get a spray of droplets, and you can get fine powders in. So there are different ways of making gas automation powders, atomized powders, but there are different nozzle designs. The earlier what I showed is pre-fall automation nozzle design, and now this is the closed coupled gas automation nozzle, where the liquid comes here and immediately after it interacts with the gas. That means the liquid and gas, if they are left open, left free, they will interact here. But in closed coupled automation, it interacts here. So it uses full high velocity gas jet energy, and efficiency of automation in this case is very high. So this gives rise to a very fine powder, and also you get very good, very low, a very narrow side distribution in this. And these are just to show that what is the market demand of these powders. Market demand of these powders with years. So this is not very important, but it just show that the demand is increasing due to the application in AM. And the second thing is, here again, you can see 3D printing metals market from 17 to 25. This is just a prediction. And here also you can see the demand for powders increases. So powder is the most important raw material for additive manufacturing, and we have to concentrate on this. Somehow the raw materials are costly, making the additively manufactured component costly. I have known some people who started up some work, and they bought some machines, but seeing the cost and the demand, they stopped those startups. So that should not happen. And this is, as I told you, for high temperature materials, this is the process, that is prep, where you have this is the material to be atomized, and this is electrode, and there is plasma, and this plasma melts the material here, and as there is a high speed motor running at around 10,000 RPM, then this liquid form here, they are ejected out due to centrifugal forces, and by the time they reach up to this point, they are solidified, and this solidified droplets and the particles are collected in this chamber. This process is mostly done in closed inert atmosphere like argon or helium. And now the properties of AM parts, this just show that the AM parts are uh, good compared to the conventionally designed parts, conventionally manufactured parts, or they may be better than that. And just one slide, I will tell you that not only additive manufacturing, but there is a new term coming up, metamorphic manufacturing. So using the cyberspace as well as the tool-less manufacturing, what is happening is now people have started passing the CNC additive. They are going to metamorphic manufacturing, and that is totally robotic blacksmithing. So it's just to let you know the term that what is going on worldwide. So here you can see that everything is being done by robot, one single person controlling every aspect of manufacturing. So this is called metamorphic manufacturing, and this person can also be shifted if somewhere else, if there is cyberspace coming in the picture. So recently, we had last year one Indo-German workshop on additive manufacturing, where 10 to 12 people came from Germany, experts in additive manufacturing, and we have many experts from India also. So I would like to bring in here the recommendations made by them. It is just 1 year old, so I hope these recommendations still hold for the country. And uh, these are they are like this. Uh, the first is manufacturing of suitable and affordable powders for AM need to be prioritized. Alternative route for powder production should also be explored. Then scientific understanding of metallurgy involved in AM, for example, microstructure evolution, solidification phenomena should be developed through experimentation and modeling and simulation, particularly the non-equilibrium kinetics and metastability. Then prediction tools for new material compositions suitable for AM processing should be developed for utilizing the technology with better acceptability. A platform is desired for big data accumulation from many machines and materials so as to make way for mass production. And next one is effective online control and monitoring of processes is required for producing reproducible and defect-free components. More emphasis needs to be given on sensing the thermal parameters during product development or during building the product. This is very important that a large pool of people should be educated on AM, because if this process has to be used widespread throughout the world, then we have to have a pool of skillful people in this, and therefore AM needs to be brought to people, and people should be educated so as to ensure availability of skilled manpower in future. Then lack of this is very I think company last year. So it was being discussed that lack of standards for materials, processes, and components made by AM should be prioritized to bring in more number of players in this technology. Otherwise, what is happening? One company makes something and it is the property of the knowledge of that company itself. Nobody else can make it. So standardization has to be a priority area in AM. And for widespread technological breakthroughs and implementation, softwares can be made available on a cloud. And the last one is the best use of the technology can be made by identifying application-driven goals, development, and deployment. With this, I end this presentation. I think this is good enough for the audience and for the students. And I thank you all.